Welcome to the 8th lecture of linear algebra. In the previous lectures, we have seen that for a system of linear equation Ax equal to 0 has more than one solution, then it has infinite number of solutions. This set of solutions has a structure called vector space. In this lecture, we will introduce the notion of vector space, which is a generalization of the algebraic structure present in R3. The study of matrices will be elaborated within this framework. What is a vector? It is a mathematical object that encodes a length and direction. That means it has magnitude as well as direction. Vectors are the elements of vector space, which is a collection of objects that is closed under addition and multiplication by scalars. For a positive integer n, Rn denotes the set of all ordered n tuples v1, v2, etc. vn, where each vi element of R. The elements of Rn are called n-dimensional real coordinate vectors or called vectors. The number vi in a vector v1, v2, etc. vn are called the components of the vector. The elements of R is referred to as scalars. A vector is often represented as one-dimensional array of numbers and it is referred to as components and it is displayed either in column form or row form. Represented geometrically, vectors typically represent coordinates within n-dimensional space where n is the number of dimensions. A simplest representation of vector might be an arrow in a vector space with an origin, direction and magnitude. Column vector. A matrix with only one column is known as column vector. R2 is the set of all vectors with two real entries. So we have two vectors here, u and v. U is having element 6 and minus 8, v is having element 0 and pi. We can also think of elements of R2 as ordered pair AB, where a and b are real numbers. Vectors in Rn, let v be the vector in Rn, v equal to v1, v2, etc. vn. If vi element of Rn, then v is called real vector of dimension n, or v equal to vector v1, v2, etc. vn, element of Rn. So v can be represented as a column vector also. Here it is represented as row vector. Now it is represented as column vector v1, v2, etc. vn, which is also an element of Rn. Now let this n equal to 2. N equal to 2 means we are choosing R2. What do you mean by R2? So means R by R. N equal to 2 means the vector has two components. The first component corresponds to the values in the x direction and the second component corresponds to the values in the y direction. So here v equal to 1, 2. So we have to take 1 units in the x direction and 2 units from the y direction. Length of the vector is the magnitude of v and theta is the angle v making with x-axis. So let us take another example. Here we have three axes which are mutually perpendicular to each other. So we are taking a vector 1, 2, 3. Means the first component represents the x-axis, second component represents the y-axis, and third component corresponds to the direction of y-axis. The vector whose magnitude is 0 is called a zero vector or null vector. If all the components of the vector are 0, then it is called a zero vector. So zero vector will be represented like this. Column vector, all the components are 0. For any vector u, we have u plus 0 equal to 0 plus u equal to u. For any scalar c, we have c into 0 equal to 0. Then vector operations. First one is addition or subtraction. Consider two vector in R2, v1 equal to 1, 3 and v2 equal to 1, 1. How will you add these two vectors? We can add the first component first. So 1 plus 1 is 2. And then add the second component, 3 plus 1, that is 4. So v1 plus v2 is a vector 2, 4. How will you represent it as geometrically? So first we can represent 1, 3. 1, 3 means 2 units in the direction of x-axis and 3 units in the direction of y-axis. So we will get a vector like this. This is our 1, 3. Then next vector is 1, 1. So 1, 1 means 1 unit in the direction of x-axis and 1 unit in the direction of y-axis. So this is the vector 1, 1. So adding these two vectors, we will get the vector which is marked as in red color. Is 2, 4. How will you subtract it? We can subtract the first component 1 minus 1, that is 0. Then subtract the second component 3 minus 1, that is 2. So v1 minus v2 is a vector 0, 2. Then how will you find addition of three vectors? Not three vectors, two vectors in R3. v1 equal to x1, x2, etc. xn, and v2 equal to y1, y2, etc. yn. v1 plus v2 means we can add the first component x1 plus y1. Then add the second component x2 plus y2, etc. Then last component is xn plus yn. Similarly, v1 minus v2 is x1, first component minus first component in the vector v2. So x1 minus y1, then x2 minus y2, then last component xn minus yn. Geometry of vectors, we can identify the points a, b in the plane with the vector a, b. So it is represented as a column vector. We can represent it as row also. Now we are representing it as column. To visualize AB by drawing an arrow from the origin to the point AB. This 3 units from the x-axis and b units from this point. To visualize minus 3, 2 by drawing an arrow from the origin to the point minus 3, 2. So minus 3, 2 means origin. That is here, this point, at this point minus 3. Then we have to move upwards 2 units because this is our y direction. So this is our vector. Addition of 2 vectors. We can visualize adding 2 vectors u, v by drawing a parallelogram, 2 of whose sides are u and v, and the diagonal of this parallelogram is u plus v. Consider 2 vectors. Here the vectors are minus 3, minus 3. Minus 3, minus 3 is plotted like this. So that is minus 3 units from x-axis and minus 3 units in the direction of y-axis. Similarly, not minus 4 minus 3 is also plotted. That is 4 points from this axis and minus 3 units from this y direction. Then we can add these two. We will get minus 3, 4. That is 1. Then minus 3 plus minus 3. We will get minus 6. That is 1 unit from x-axis.
Scalar multiplication. We can visualize scalar multiplication Cu by stretching or stringing u by a factor of c. If c is negative, then Cu points in the opposite direction from u. Consider this vector u. So stretching means we will stretch by a factor of c units. So we will get a vector like this blue vector. Similarly, here c is negative. This is our u and c is negative, negative 3. So then Cu points in the opposite direction from u. Higher dimensions. For any positive integer n, the set Rn contains all n tuples of real numbers a1, a2, etc. an. Representing this as a column vector, we will get a1, a2, a3, etc. an. In general, u equal to u1, u2 and v equal to v1, v2 and c is a real number. Then we can represent u plus v like this. We have to add the first components u1 plus v1, then u2 plus v2. Then scalar multiplication. We have to add c with each and every elements present in u1. So c into u1, c into u2. Vector addition and scalar multiplication operation are performed component wise. Dot product. Let v equal to x1, x2, etc. xn, v2 equal to y1, y2, etc. yn, v1 dot product v2 equal to x1, y1 plus x2, y2, etc. xn, yn. So it can be written as sigma I equal to 1 to n xi, yi. Example. Let's consider 2 vectors v1 and v2. v1 equal to 1, 1 minus 1 and v2 equal to 2, 3, 1. So v1 dot product v2, we will get 1 into 2, that is 2, 1 into 3, that is 3, minus 1 into 1, that is minus 1. So then add these terms, 2 plus 3 minus 1. So we will get a number 4. Length. Let v equal to x1, x2, etc. xn. Length of a vector is denoted like this and it is square root of dot product of v. So we will get x1 square, x2 square, etc. xn square. Example, v equal to 1 minus 1, 2. So length of vector equal to, we have to take the square root, then take the squares and then take the sum. So 1 square minus 1 square plus 2 square, that is root 6. Angle between two vectors. Let v1 be to element of Rn. The angle between v1 and v2 equal to theta equal to cos inverse dot product of v1, v2 divided by product of length of v1 and v2. Vector space. A vector space over R is a set V of elements called vectors together with two binary operations called vector addition and scalar multiplication if the following hold. Note that vector multiplication does not hold. So it must satisfy the following properties. For all UV element of Rn and all scalars CD, commutative properties, associative property, there exists a zero vector, then additive inverse is there. It must satisfy distributive property and there will be one identity element. Closure property will also satisfy. Examples. Vector space Rn over R. Let V equal to Rn be the set of all ordered n tuples. The vector will be a1, a2, etc. an for every ai element of R. Let vector addition and scalar multiplication is defined as we have two vectors a1, a2, etc. an and the other vector is b1, b2, etc. bn. It is an element of Rn. So how will you add it? We can add the first component a1 plus a2, then add the second component a2 plus b2, Similarly, last component an plus bn. So this will be an element of Rn. Why? If we add two real numbers, 2 plus 3, it is 2 plus 3 is 5. 5 is again real number. So it will be a real number. Then scalar multiplication, lambda a1, a2, etc. an. So we have to multiply this lambda with each and every components of this vector. That is lambda a1, lambda a2, etc. lambda an. So lambda will be an element of R. It is a real number. So this vector is again an element of R raised to n. Next example, polynomial space Pn of t over R. Let Pn of t denote the set of all polynomials of degree less than or equal to n. The set of all polynomials P of t equal to a0 plus a1t plus etc. as t raised to s, where s less than or equal to n and ai element of R. First, we need to check whether the closure properties are satisfied. So we can consider two polynomials P1 of t equal to a0 plus a1 of t plus a n t raised to n, a P2 of t equal to b0 plus b1 t plus bn t raised to n. So adding two polynomials, we need to add the first component, that is a0 plus b0, then add the second component a1 plus b1 into t plus last component is an bn t raised to n. So this is again a polynomial, so it will be an element of pn of t. Then we have to check whether the scalar multiplication is satisfied. So lambda p1 of t equal to lambda a0 plus lambda a1 t plus lambda a2 t square plus etc. lambda a n t raised to n. This is also an element of pn of t. So closure property with respect to addition and scalar multiplications are satisfied. Polynomial space is a vector space. Next example, metric space M of order m by n. So we can consider set of all m by n matrices with elements from R. So consider two matrices A1 and A2 with elements A1, B1, C1, D1, E1, F1. A2 with elements A2, B2, C2, D2, E2, F2. So we can add the elements first row, first column, A1 plus A2 and B1 plus B2, C1 plus C2. So after adding these two matrices, we get a matrix with order of 2 by 3. Order of A1 and A2 is also 2 by 3. Again, if we multiply this matrix with a lambda, again the order of that matrix will also be 2 by 3. Therefore, matrices is a vector space. Another example, solution of Ax equal to 0 form a vector space. V equal to x element of R raised to n such that a mn xn equal to 0 m. This is called null space. X element of Rn and R element of n is a vector space. So that is already proved. All the properties are satisfied. So it is a vector space. So we can consider two elements in X, that is x1 and x2 element of vector space. So we are substituting in this equation, we will get
A of x1 plus x2 equal to 0. Also, A of lambda x1 equal to 0. That is, scalar multiplication is satisfied. At the same time, vector addition is also satisfied. Therefore, the solution of a homogeneous system forms a vector space. It is to be noted that the solution of non-homogeneous system is not a vector space. V element of Rn forms a vector space. Therefore, it is called vector subspace. Definition of subspace. Let B be a vector space over R. Let W be a subset of V. Then W is a subspace of V if W is itself a vector space over R with respect to the same operations as in V. Criteria for identifying subspaces. For every UV element of W and lambda element of R, the following closure properties should hold. U plus V element of W, lambda U element of W. Trivial subspaces of a vector space V are the set 0, the whole set V itself. An example, U equal to set order triple A, B, C such that A equal to B equal to C. Subset of R3 is a subspace of R3. R3 is a vector space. We had already proved that R3 is a vector space. So ABC is a subspace. So we can select A because A equal to B equal to C. So we can select A. So all the elements are A. This is the element of U. Again, another element we had selected is B. So all the components of the vector are B. So first we have to check whether the vector addition is satisfied. So A plus B, A plus B, A plus B. Then we have to check whether the scalar multiplication is satisfied. Lambda into first vector is A. So lambda A, lambda A, lambda A element of U. Both the scalar multiplication and vector additions are satisfied. Therefore, U is a subspace. Another question. V equal to x1, x2, element of R2, x1 is greater than or equal to 0 and x2 is greater than or equal to 0. Does V form a vector space? No. Why? V is not a subspace of R2 because minus 1x not an element of V. Here it is given that x1 must be greater than 0 and x2 is also greater than 0. So negative quantities are not allowed. Suppose this lambda is minus 1 and the vector is 1, 2. So if we are multiplying this minus 1 with this vector, we will get minus 1, minus 2. But this is not an element of this B. So this B does not form a subspace. Consider the vectors of the form s plus 4t, 3s minus t, 5s plus t, 2t, transpose S and T element of R. Is the set of all such vectors form a subspace of R4? So consider this vector S plus 4t, 3s minus t, 5s plus t, 2t. This is equal to separating the S term and T term. We will get two vectors like this. So we can select two such elements. So just change the coefficient. There is no change in the elements of this vector. So first element is this one, S1 1350 plus T1 4 minus 1 1 2, and next element is S2 1350 plus T2 into 4 minus 1 1 2. Adding will give, we can just add the coefficients. There is no change in the elements. So we will get an element like this. So this will be an element of R4. Again, scalar multiplication means lambda into one element, first element. So lambda S1 1350 plus lambda T1 4 minus 1 1 2 is also an element of R4. As a conclusion, in this lecture we had studied about vector space and vector subspaces. So vector subspace means it must satisfy the closure properties, vector addition and scalar multiplication. Thanks for watching.